Okay, there we go. So, welcome everybody who's watching online. I'll say that again. Sorry, this is like the second time that I'm doing this, so sorry. Okay, so we're doing origins of Earth's oceans, because it's oceanography, you want to know where the oceans came from, right? So that's an important thing to figure out. So here's a picture, this first picture you see. This is from the Earth way back. You know, Earth probably began around like 4.5 billion years ago. Okay, we know that. How do we know that at all? Does anybody have any idea why scientists think?
Because of the crystal, right, that they found, it was like 4.3 billion.
Sure, but why do they? How are they even able to like? Yeah, radioactive. So all these things, like people say, oh, Earth is this old, that old. All that is based on radioactive decay. So elements decay at a certain rate, radioactive ones decay at a certain rate, and we're able to figure out, like, okay, this much of this isotope is left, this much of that isotope is left, so therefore this rock must be X number of years old. Okay, so that's what this is all based off of. Not all this, but that's where we get those absolute dates, okay? So we think 4.5 billion years ago we think Earth started. Or at least started in the sense, it got accreted together. Now what, I say it accreted together, came together. What material came together to make the Earth? Were there always just planets going around the sun, or was there always a sun? What's that? Oh, the atoms? Yeah, atoms came together. Well, it was all from meteorites, right? So all meteorites are is it's just all the dust and rocks that were spinning around the sun in the early solar nebula, right? So all those meteorites came together, and we have the different planets. That's why I don't know if I mentioned this in the last lecture. Maybe I did, but I think that I might have mentioned that the Earth has the same composition as the meteorites. Did I mention that at all? Or maybe I didn't. Okay, well that happens to be true, and it's because Earth came together from the different meteorites. Okay. Now this little picture is from the Archean, and it's probably maybe 3.8 something like that billion years ago, and we think that's about how old the oceans are. Something in there. So we'll kind of talk about some of the evidence of why that is and why we think the oceans are that old, et cetera, et cetera. But you can see this picture of the Archean shows oceans. Okay, so Earth is an ocean planet, so 71% of its surface is covered with water. We already talked about that. Okay, make sure you know that number because that's on the test, and it's probably on the final exam too. So make sure you know that. Okay, and I'm going to get my lecture assignment packet. I printed one for myself too, so that I can go along with this as well. Okay. So this is actually, by the way, the color of the ocean. So this is a true light color image of what the different ocean colors are. And we have we already talked about our 5 oceans, right? 3 big ones: Pacific, Atlantic, Indian, and then the Arctic and the Southern. I hope you remember all those. This is just kind of going over important things to remember, right, from last lecture. Now, as far as we know, Earth is the only planet in the solar system with liquid water oceans like this. Okay, we'll go over some possible other non-planetary bodies actually that might have some. But as far as we know, Earth is the only planet with oceans, okay, with liquid water. So, as far as we know, actually, as a matter of fact, it's the only planet in the whole universe that we know of that that has an abundance of liquid water. Okay, there is some, like on Mars, we've discovered like some soil moisture, maybe you could say, but it's kind of a long way from being like an ocean or a body of water, right? We'll talk about some other things though. All right, so Earth is kind of a special place. You might have heard this term before called the Goldilocks zone. Has anyone ever heard about that before? The Goldilocks zone?
It's habitable.
Yeah, it's a certain zone, in a solar system that is habitable, right? That could have life and could have liquid water on it. Okay, so there's the definition of it right there. But you know Goldilocks, what happens in the Goldilocks story, right? The three bears come in. Oh wait, no, the three bears don't come in. The three bears leave, and they got their forage there. And, you know, Goldilocks comes in, and you know, one's too hot, one's too cold, but the other's just right. So we're looking for the part of a solar system that's just right for liquid water, right? And what can happen? You know, well, you can be too close to the sun, right? If you're too close to the sun, why is that problematic for liquid water? It's too hot, right? It could be too hot. If you're too far away from the sun, what happens? It's too cold, right? It's just like the Goldilocks story. So then you don't have liquid water, you have frozen. You have some kind of frozen ice, right? There's other parts of this, though. You have to be the right distance from the sun. You have to have also a stable enough orbit. You know, that's another factor here too. Some planets have very erratic orbits. They change a lot. You know, they will become maybe more elliptical one year. They'll become more circular another. They'll have this varying distance from the sun that is very unstable, and it's not really conducive to life or to liquid water. So it has to have a stable orbit, no seasonal extremes. You know? Seasonal extremes. What causes the seasons here on Earth? We talked about that, right? What causes there to be seasons?
Equinoxes.
Well, the equinoxes are kind of part of the seasons, but it's the axis. It's the tilt of the axis, right? If you have, you know, there are some planets that have an extreme tilt. There's actually some planets like Uranus that are tilted almost 90 degrees, so they have the most extreme seasons you could possibly have, right? So all those things would not be conducive to life or to liquid water on the surface, okay? Another thing is you have to be about the right size as well. So if you're too small, you don't have enough gravity to hold liquid water onto your surface, because when water evaporates and turns into a gas, if you don't have enough gravity to keep that water vapor close to the surface, it'll just evaporate and it'll go into outer space and it'll be lost. So does that make sense? That's why the moon, does the moon have any water on it? Bone dry, right? It's totally bone dry. Part of the reason for that is it's so small, it doesn't have enough gravity that even if there was water there, it would just be lost. Okay? It doesn't have enough gravity to keep it near its surface. So we're actually, I don't know if you know this, we're the biggest of the terrestrial planets. Right? We're the biggest of the terrestrial planets. So we have a lot of gravity, so we have enough to keep the liquid water close to us. Okay? So there's a lot of things, there's a lot of aspects of our planet that have to be just right for there to be liquid water and for there to be life too. Right? So everything just kind of had to be just right for there to be life here on Earth and for there to be water here on Earth. And that's why, you know, you look at our other friends in the terrestrial planets, right? Mercury, Venus. Venus is very similar to Earth in a lot of ways, but there's no liquid water there. Mars, there's no liquid water there. Okay, so does that all make sense? So that's, I actually gave you, for number 3, I gave you 3 characteristics, right, of a planet, but you just have to put 2. Okay, so let's see, our planets in Goldilocks. Oh yeah, this is another thing too that's kind of interesting. We're also in a relatively, fourth thing, it's part of kind of the Goldilocks zone. We're also in a relatively stable part of our galaxy as well, because you know there are parts of the galaxy, the whole Milky Way galaxy, that are inundated with supernova, with exploding stars, and the radiation that comes from those exploding stars and the winds that come from it are able to wipe out, you know, any volatile elements like H2O off of the surface. So that's yet another aspect of it. You know, you have to be in the right part of the galaxy. You have to be in the right part of the solar system as well. So there's a lot that goes into it, right? So there you go. There's a GIF of a supernova. Oh, is it GIF or GIF? I always say GIF. I always forget if it's GIF or GIF. Does anybody know what I'm talking about? You have no clue. They call it a GIF.
They say GIF, but
Yeah.
I'll
That's
GIF.
what it's spelled like GIF.
Graphic.
What's that?
It's GIF. The G stands for graphic.
it's
Right, that's a good point.
It should be GIF.
It should be GIF, but they say GIF. It's one of those things. Anyway, all right, so Everything's just right for liquid water, right size. It allows for interior convection and stable degassing of the interior. So that's another thing. What's happening in our mantle all the time? You already learned this. What's happening in our mantle? It's convection, right? And that convection of the mantle, we just happen to be the right size to allow mantle convection. Because if we were too small, what would happen? All the heat would be lost from our planet very fast. That's actually what happened on Mars. Mars is pretty small. It's only about 11% of Earth's mass. The heat was lost very fast, so it never really got into a stable regime of mantle convection and plate tectonics. And that allowed, now that's important. Why? Because a lot of the water that came from, it's on our surface in the oceans, where did it come from? It came from the interior of the planet. So there were minute amounts of water that were included with the meteorites that collided with Earth. A lot of that water was trapped in the mantle, and it couldn't be released unless we had this stable mantle convection that allowed for this, degassing of the mantle over billions of years, which is a process that's still occurring, right? There's still this slow process of degassing of the mantle. Okay, we couldn't have had that if we were too big or too small. So we're just the right size for plate tectonics to occur as well, and for mantle convection to occur, and therefore also to have this nice, stable, long-term release of heat and release of water from our interior. So does that all make sense, what I explained here? Okay. So it's just kind of amazing, like how much there is to this. It could have been so easy for one thing to go wrong, and then we wouldn't have had liquid water, we wouldn't have had life here on Earth, and none of us would be here right now.
Maybe someone's in charge of it.
Yeah, sure. So, you said it, not me. But anyway, we have 97.2% of all Earth's water is actually in the oceans. Okay. So 97.2. So vast majority of Earth's water is in the oceans, and that's a very important number. You want to know that, right? You want to know that. Now, of that water that isn't in the oceans, it's kind of crazy, but look. So we're going to take that's the fresh water right there. Y'all see that? That little red, teeny weeny little pie slice is the fresh water of Earth. And look where most of that fresh water is. Can you see this? It's mostly in glaciers. About 75% of it's in glaciers. So it's kind of amazing. If you think about this, we need water, right? We need fresh water. We can't do too much with salt water, right? Can't do too much with it. We need that fresh water. Most of the fresh water is locked up in ice sheets, right? So we only really use just a tiny, we only have access to maybe like 0.65% of the water of Earth is really useful for us as fresh water. So there's so much water on this world, but we can only use a very small portion of it. Like I said, not even 1%. So that's why, some places, even in Texas, water is a big deal. Even here in Corpus Christi, water is a big deal, right? We have problems providing enough water. That's why they want to do these desalinization plants and things like that. Oh, and by the way, that's a great topic for the research paper too. That might be something if you want to do the research paper. That's a great thing to look up because that's very pertinent to what's happening here in Corpus and what's going to happen to our bay and things like that. So it's a great topic to read about. I love reading those. Somebody did that last semester. I love reading that because, like I said, it's very pertinent to what's going on here in Corpus Christi. So, do y'all hear about those things, desalinization plants? Right? Yeah. So
I need something. You look at the water report in Corpus Christi.
Yeah.
And it's got like cyanide, fecal matter,
Oh,
all
sure.
these weird things.
Sure. Oh yeah. Yeah, water's a big issue, right, for society, because there's actually not some places are blessed with a lot of water,
Sure.
but some places are not. In Texas.
Drinking Rome's water right now.
What's that?
I think we're drinking Rome's water right now.
We're drinking what water?
Rome.
Rome?
Remember Rome had the lead pipes?
Oh, yeah, that's true.
You know?
Yeah.
Everyone drink that.
Now, another kind of thing that's a little bit interesting here, I wanted to show you. Oh, yes, this is number 5. I say, how much water is stored in the mantle? Well, I was kind of suggesting to you, a lot of Earth's surface water, ocean water, probably came from the mantle. There's some other ideas about sources too, but it probably was degassed from the mantle by volcanism over the years. So how much water is down there? Well, there are some people that think, we don't know exactly, but there are some people that think that there could be up to 50% of Earth's total water is still down in the mantle. So there's a whole other, if you will, ocean. It's not really an ocean. It's not like there's a pool of water down there. There could still be a lot of water down there in the mantle. Now, like I said, it's not liquid water. It's not like there's droplets of water or steam or it's not like there's an ocean down there underground or anything like that of liquid water. But a lot of it's trapped in minerals. So this mineral especially, this is it doesn't exist on the surface here. So there's a lot of it in the Earth's mantle. It's called ringwoodite. It's actually kind of pretty, isn't it? It's like kind of bright blue. Ringwoodite actually contains quite a bit of structural water. So water is part of its mineral formula. Water is part of its mineral formula. There's a lot of minerals that are like that. Okay? They have water as part of their structure. So ringwoodite is an example of that. It actually has water in its crystal structure. And so that's how water is contained in the mantle. Okay?
Why doesn't it exist on the surface, you said?
Because it just, you need to have very certain pressure temperature conditions.
Oh, so like you can bring it out, but
You could bring it out, yeah. But it doesn't form at the surface because it's the same thing like with diamonds. You know, diamonds aren't stable. It's kind of funny because people say like diamonds are forever. Not forever at all. They're actually very unstable at the surface. If you were to put, this is true, don't do this, but you could take a diamond and put it in maybe like a pizza oven, get it maybe 200, 300 degrees Celsius and break it down, right? It would turn into, because all it is anybody know what a diamond's made out of? Yeah, it's just carbon, right? It's absolutely pure carbon, just like your pencil lead. And if you were to bring it to that high temperature, what would happen? It would probably decompose into graphite. Would that be sad, right? Yeah, so don't get your diamonds too hot. Yeah, don't get your diamonds too hot because they're not forever. They will decompose. They can decompose. Because they're only stable at high pressure. They form at high pressure, right? So same thing with ringwoodite too. Okay. So anyway, this is another example. Sometimes you can have little bits of water trapped. And speaking of diamonds, this is a little bit of water that's trapped in a diamond. That actually, by the way, those are called inclusions. For those of you who know anything about gems and diamonds, they're actually a problem. They lower the value because it disturbs the clarity of the diamond. So, but it's actually a very common thing, right? There's little bits of water or gases that get trapped within minerals called inclusions. Okay. So I'm just giving you some ways to show you how the mantle can hold water. Okay, because I know it's kind of a weird idea that there would be water in the mantle. Because it's hot, right? It's very hot down there. Remember I was saying, like in the mantle, it's white hot. You like burn your eyes if you saw it. So how could there be water when it just evaporated? Well, I'm giving you some examples. Okay. So anyway, just some basic facts here about the oceans. Okay. Covers 331 million square kilometers. Average depth is 3.7 kilometers deep. Okay? That's a very important thing. So you can round it off to 4, but you should know. Definitely on the final exam and for the midterm, I'm going to ask that. I ask a lot of just basic facts. I want to make sure you know the basic facts. You should know how deep the oceans are. Okay, it's about 4 kilometers. So make sure you know that. About 4 kilometers on average. There's 1,000,000 trillion gallons of water, which is the same as a quadrillion. Oh no, it's more. It's 1,000 quadrillions. That would be more. Yeah, it's a lot of water. Okay, So where did the oceans come from? Okay, so this is kind of part we go from the stars to the seas. How do we get there? So just kind of starting at the beginning. All matter on Earth, and all matter in the universe, all matter in the solar system, and in addition to that, this is kind of one of these things very tricky and strange to think about. All space, time, right, volumes, matter, energy, it all had a very definite starting point. Right? So you've probably heard of the Big Bang Theory, right, besides the show. The Big Bang Theory is actually a theory that tries to explain, it's a cosmological theory, okay? It explains what the origin of the universe is. So just to kind of give you an idea of what the Big Bang Theory actually states, it states that all space, time, matter, and energy originated at a single point called the singularity. So there was a very definite starting point, a very definite starting time. There was a time zero. And that all matter and energy existed at a single point in a point of infinite density. And now there's a lot of evidence for the Big Bang, which is difficult to understand for, an introductory science course. But I'm going to present one kind of argument for it so that you have some idea about where, we're not just pulling this out of thin air, right? So I'm going to present one argument for it to kind of explain it. Okay, so Big Bang Theory was actually developed in 1927 by this scientist. You can see Father Georges Lemaitre. He's a Belgian priest and scientist. He's there standing next to Einstein. And he came up with the theory in 1927. And it's been, roundly accepted in its original form since that time with very little modifications. It's stood the test of time pretty well. It's getting close to being 100 years old now, actually. All right, so why do we think this is true? Why do we think the Big Bang happened? So let me explain a little bit. You've probably heard of this scientist. Well, you probably heard of the telescope named after this scientist. What's the really famous space telescope? Hubble, right? And that's actually named after a very famous American astronomer named Edwin Hubble. Right, so there he is. And one of the things that Edwin Hubble did that was so important is that, remember the Big Bang at this time, in the 1920s when it was first originated, it was just a theory. Okay, and it didn't have a lot of, or maybe I should say actually it was just kind of a hypothesis, and it didn't have a lot of data and experiments and observations backing it up yet, right? So it's like a hypothesis. So what Edwin Hubble did is he provided a lot of those observations that backed up the theory, and that's why we now accept it as, almost as a, we accept it as a theory that explains the origins of the solar system, right? Or origins of the universe. So let me explain a little bit how this works. One thing that Hubble noticed is that when you look at stars from far away, the light that comes from the stars is a little bit more red than it should be. It's a little bit more red than it should be. I'm looking for a spectroscope. That's not a spectroscope. I should have gotten this out before the class. I know that we have one. Where is it? Spectroscope. Is this it? No. In here. I had this out at the beginning of the semester. Okay. Well, hopefully I can find it a little later. But anyway, The light that comes from distant stars is a little bit redder than it should be. Does that make sense to you all? Okay, it's a little bit more red than it should be. What's kind of cool is that we can actually, did you ever wonder how we know the composition of distant stars? You ever wonder how we could possibly know? Have we gone to another star and like took a little scoop and took it back to the lab and analyzed it, see what it's made of? No, we never did that. So how do we have any idea? How do we know anything at all about distant stars? Like, how do we have any information about it at all? What's that? It's based on the light. It's all based on the light that comes from that star. Believe it or not, we can actually figure out exactly what that star is made out of, even light years away, 100 light years away. We can figure out exactly what that star is made out of, the elements in that star, based only on the light that comes back from it. And if I could find my spectroscope, I could show you how. I have one around. I just have to find it. But yeah, we use spectroscopes. And it breaks down the light kind of like a prism, right? You've seen a prism before, right? It breaks down. We use a spectroscope. It's just a prism, and it breaks down light from the distant stars into its different wavelengths. Okay, so the light that comes from distant stars is redder than it should be for the size of the star. Okay, and this is what's very strange. The light, the further away that star is, the more red the light. The redder the light is. Okay, the redder it is. So we call that kind of anomaly, that light that's redder than it should be, we call that a red shift. Has anyone ever heard that term before, a red shift? Okay, we call it a red shift, and what it means is that the light from a star, a distant star, is a little bit redder than it should be. It's shifted to a little bit redder wavelength. And that made everybody at the time, in the 1930s and 1940s, say, that's very strange, right? It's a very strange observation. How do we explain that? Well, this is how you can explain it. The star that you're looking at is moving away from you. The star that you're looking at is moving away from you, and that will make the light appear more red. This is called the Doppler effect. So you've probably, actually, you know very well what the Doppler effect is. You've probably seen something like this before. Whoops, so this could, let's close this because it'll play. Yeah, there it goes. I'm sure you've seen this before in your life. So this guy has got a trumpet, and he's going to blow his trumpet when he's in the car. You're probably wondering what this has to do with stars, but I'll explain. Okay. Okay, remember what that sounds like. It's playing one note. Okay, now, you all remember what that note was, right? You can hopefully hear it in your imagination. Different, right? Higher pitch, higher frequency. He passes you, and I'm sure that's happened before to you, right? A siren is going off, or a horn, it goes, right? It sounds like that, okay? So, the frequency that you hear changes with whether the car is moving towards you or away from you. I don't know why I can just do this. Why am I going over here? Oh, because it doesn't work. That makes perfect sense. Okay. So when it's moving, oops. So when something is moving towards you, you get a higher frequency, whether it's light or sound, you get a higher frequency. When it's moving away from you, you get a lower than actual frequency. Well, that's exactly what's happening. This is exactly what's happening to every star in the universe. They're all redshifted. All of them. They're all redshifted. They're all moving away from us. Do you see what I mean? Nothing's moving closer together. I mean, I don't mean the atoms of your body. I mean like the stars. None of the stars, or I should actually say the galaxies, okay? Yeah, let me clarify that. The stars in other galaxies, they're all together completely moving away from us, okay? So that means that every galaxy is moving further away from the other galaxies. A way that you can visualize this, and maybe I should have brought a balloon. But imagine I start blowing on a balloon and I put a bunch of little points on the balloon, okay? And they all represent stars. And then I blow the balloon up and I expand it. Every point would be moving away from every other point, right? Does that make sense? If you put those little dots on the balloon, they represent the different galaxies, and you start to blow up the balloon, every galaxy would be moving away from the other galaxies, right? Every galaxy would be redshifted in relativity to every other galaxy. Okay? That's what's happening. And that's the evidence. That's why they think that the universe is constantly expanding like this. Okay? And what you can do with actually what Father George Lemaitre did that was so groundbreaking is he actually solved the different matrix calculus equations that gave the directions of the different, it's complicated. But he showed that if you kind of reverse time, all of the galaxies would have originated at a single point. You see what I mean? Which is why we think, if you put the whole video on reverse and rewind it, it would all come to a single point, which is why we think everything seems to be emanating from this single point that occurred, and everything would have come together 13.7 billion years ago. So that's why we think the Big Bang is real. It happened. So I hope I gave you some kind of qualitative understanding of why we think that. It's not just pulled out of nowhere, right? Does this all make sense? Do you believe me? It's crazy. It's kind of crazy, right? It's kind of. Sometimes. It's like truth is stranger than fiction. People say that. I think that's true. Okay, and by the way, red, you all see this like electromagnetic spectrum before? Have you all seen this before? EM spectrum, visible light spectrum? Well, you've seen a rainbow, right? Okay, so rainbow, and I hate it when people draw rainbows and the colors are wrong. Because you can't just I like how the red looks next to the purple. No, you can't change. It goes in a very it goes red, orange, yellow, green, blue, purple, right? Violet, ultraviolet. Okay, so red is kind of that longer, lower frequency, long wavelength, lower frequency. So that's why the frequency changes. There's a red shift. We get redder light. It's because the frequency is lower than it should be because it's Doppler effect. It's moving away from us. Okay, it all makes a little bit of sense. You don't have to understand it perfectly, but just a little bit of sense. Okay, so Big Bang. One reason we believe it is because, because of redshifts. Okay, so were you all able to explain briefly number 7? Briefly explain the sentence or two the Big Bang. You all able to do that? Okay, and number 8, were you able to kind of explain what a redshift is? Okay. Just, the light coming from distant galaxies seems to be shifted a little bit more red than it should be. And it's showing that those galaxies are moving away from us, and that everything would have emanated from a single point. Kind of.
But how does it support the Big Bang theory?
It's because redshifts show, the fact that all galaxies show redshifts shows that all of them are moving away from us. They're all moving, so all galaxies are, and it's not that we're the center of the galaxy, center of the universe, it's that everything is moving away from everything else, and that's because the universe is expanding, which is part of the Big Bang theory.
So we're also moving away from things?
Well, our galaxy is moving away from other galaxies. So yeah, I said this one time.
It's not like just Earth is doing that, it's like everything's kind of.
Yeah, the galaxies are sort of self-contained. So it's
Yeah.
not like, like I said, like it's not like the atoms in your body are moving away from
No,
each other.
yeah.
It's not like Earth is moving away from the other planets. And it's not like the other solar systems in the galaxy are moving away from each other. But the galaxies themselves are. So it's kind of more on a galactic scale that we're talking about, the expansion. Does that make sense? Kind of. It doesn't have to make perfect sense. It doesn't have to be perfectly clear, but I just hope you have some qualitative understanding of it now. Okay, but just know that, time and space, matter, energy seems to have a single origin at a single point in time. All right, so what happened after the Big Bang? So immediately following the Big Bang, we had within less than a second, we had the first atoms put together. So we had the first atoms. And those atoms were overwhelmingly hydrogen. Okay? And still, to this day, what's the most popular element out there?
Hydrogen.
Hydrogen, hydrogen, hydrogen. Even in our solar system, it's 99% hydrogen. It's more than 99% hydrogen. So it's like, that's the element, It's the most popular one by far. Okay, so you got that. So yeah, and that. Hey, it only took. Oh no, it took a whole 100 seconds to make a hydrogen atom. So sorry, I said that. Thought it was less than a second. Yeah, we think then less than 2 minutes we had the first elements. Yeah. And then 100 million years later, we had the first stars form. But 13.7 billion years ago, so number 9, saying how long ago do we think this Big Bang occurred? I think it's 13.7 billion years ago. All right, so you got all this hydrogen, you got the Big Bang, you got all this hydrogen. How do you get a star? Right, that's what we want to know. So we need our sun. We need to know the origin of the sun, to get origin of the solar system, get the origin of Earth, so we get the origin of the oceans. Okay, so we got our hydrogen. How do we get to a star? So this is explained by the nebular hypothesis. The nebular hypothesis was first developed by Immanuel Kant way back. Immanuel Kant was actually a really famous philosopher, actually, not so much a scientist. Developed this hypothesis. This is way back before the 1800s. This is in kind of the beginning of the Age of the Enlightenment, around the French Revolution times. And came up with nebular hypothesis. And actually, that's still the predominant hypothesis that explains how we go from hydrogen to a star. So let me explain a little bit nebular hypothesis. So what nebular hypothesis says that we start off with a nebula. Guess what nebula means? It just means cloud. It's just Latin for cloud. Okay, so it just means that we start off as a cloud of mostly predominantly hydrogen. Now, our nebula that ended up creating the solar system was a little bit different. Okay, it had some other things in it, and I'll explain that later. But it's predominantly hydrogen. It's 99% hydrogen. Okay, so once that cloud gets so large, it gravitationally collapses. So that means that there's kind of a snowball effect. So the way that gravity works, is that the bigger you are, the larger your pull, right? The bigger you are, the larger your pull. So there's kind of a snowball effect. The nebula gets bigger, it pulls in more mass. That makes it bigger. And so then it has more gravitational force, and it pulls more stuff in, and more stuff, until you eventually get this out of control snowball effect. And you get so large that it's able to condense into a star. Okay. So what happens is that I kind of show you. I thought I had another GIF or GIF that kind of shows this. No, I don't. No, I got rid of that. I really liked it. But anyway, what happens at a certain point is that when the hydrogens get so close together, they will finally have a nuclear reaction. Finally has a nuclear reaction. And it's a fusion reaction. Fusion means that it binds together. Okay? So when the pressure inside the protosun increases so much, gets so large and so much mass, the hydrogens in the center will be under such pressure that they fuse together, and you get 4 hydrogens. They fuse together, they release a lot of energy. Hydrogen bomb, right? You've all heard of a hydrogen bomb? That's what we're talking about here, right? It's the energy from like a hydrogen bomb, right? The hydrogen bonds together, makes a fusion reaction, it releases a lot of energy, and it makes helium-4. That means a helium that has a mass number of 4. That means it has 2 protons and 2 neutrons. Okay? So hydrogens bond together, and it gives you a helium-4. And that's called, has a few names. It's called hydrogen burning. Hydrogen burning. It is a form of something called nucleosynthesis. Just means the nucleosynthesis just means the synthesis of a nucleus, right? So, the nucleus of an atom, protons and neutrons, right? Okay, so what isotope of what element is synthesized by the hydrogen burning process? Number 11 is helium-4. Helium-4. So that explains hydrogen, and that explains where helium comes from. But we have a lot of elements in the periodic table, right? A lot of elements. So I explained the origins of hydrogen. Where did hydrogen come from? Big Bang. Where did helium come from? Where does helium come from? It comes from hydrogen burning. But there's so many other elements. Where do they all come from? Okay. They come from that nucleosynthesis process that occurs in the cores of stars. So we'll explain this a little bit more. Now, helium can come together. 3 heliums, we call this the triple alpha process. 3 heliums can come together. Helium-4 plus helium-4 plus helium-4, and that gives you carbon-12. Which makes sense because 4 times 3 equals 12. Gives you carbon-12. Carbon has 6 protons, 6 neutrons. Okay? And it releases a lot of energy. So this is what creates all the energy from the sun. It's all these nucleosynthesis processes. Okay? Hydrogen burning. This is the triple alpha process. Okay? That's what creates all of the sun's energy. And then carbon can burn. We call that carbon burning. Carbons can combine. And it gives us oxygen and neon and sodium and magnesium. So you see how these different elements are combining? They're burning, they're giving off energy every time they combine. And that's where you get all these different elements. So if you ever wondered, like, where did all these different elements come from? We have different elements that make up the rocky planets and everything. It all comes from this nucleosynthesis. Now this is able to happen. Okay, so you all got number 12, right? It says, what nuclear reaction forms carbon in a star? Triple alpha process, that's right. What isotope is carbon is created by that? Carbon-12, that's right. So there's the process. It's really not that. It's really, you don't even have to put helium plus helium plus helium. You just put 3 heliums go to carbon-12, and that's okay. You don't have to write out every detail of that, but you could just say, 3 helium-4s give you carbon-12. Okay, that's where our carbon comes from. So that's where the carbon. That's like all the carbon in your body. Isn't that crazy? All the carbon in your body. Where did it come from? It came from this nucleosynthesis process. At some point, those atoms were being formed in the core of a star. Weird to think of. And here's a bunch of other reactions, right? And so it's kind of cool because you see this, hydrogen burns on the outside and helium is created on the inner, carbon burns, neon burns, oxygen burns, and it all burns until it gets to iron. And then everything stops at iron. The whole train stops at iron. So it's like a big machine. A star is like a big machine that takes hydrogen and turns it slowly, step by step, it turns the hydrogen into iron. And then the train stops. Everybody gets off at iron. And every step you release energy. So every step you release energy. You turn the hydrogen into helium, it releases energy. You turn the helium into carbon, it releases energy. You turn the carbon into neon, it releases energy. Every step you release energy. And that's what powers the sun, and that's what powers all the photosynthesis and even powers you, right? Because all the food you eat, ultimately it comes from photosynthetic plants or something that ate photosynthetic plants or something that ate photosynthetic plants, right? You know what I mean? Yeah, like a cow, you have a steak, ate grass, where the grass gets energy from, got it from the sun. So it's all coming from this, ultimately. So does that all make sense? All this stuff? But it all stops at iron. A star cannot make, it can do a lot of things, but a star can't make anything beyond iron. Can't do it. It's impossible.
Aren't those also just like the basic like elements for everything pretty much?
Yeah, for a lot of them, but I mean, there's still a lot of elements that, those are the most common elements. Like you actually might be looking at this, like some of these elements sound familiar. Like, do you notice how some of the most prevalent, all the prevalent elements in our planet are here? Iron, silicon, oxygen. You could see over here, right, carbon burning makes magnesium. Okay, so things, once you get heavier than iron, things get more rare. The elements get more rare. Okay, so you can make everything up to iron. Is there anything in our solar system or on Earth that is heavier than iron? That's like got a higher elemental number than iron? Like, do we just stop here? You see, go like 1, 2, lithium 3, beryllium 4, boron 5, carbon 6, 7, blah 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 to number 26, iron. Can we get anything heavier than iron? Is there any? Does anybody have any copper pipes in their house? Does that not exist? Copper pipes exist?
For like something.
Yeah, sure. I just mean we have copper, don't we? We have mercury, gold. Does anybody have any gold? Gold earrings or rings or something? So we have all this stuff, right? So where's all this junk come from? We have all these things. Where's that all of that? Can a star make that? Can you make it in a star? Can you make platinum in a star? I wish. No, you can't. Okay, so where does all that come from? So you can only make, a star can only make it up to iron from nucleosynthesis, stellar nucleosynthesis. Okay, so it can only go up to iron. That's because when you try to combine things to make things heavier than iron, it takes energy. You have to put energy in to get heavier elements. Now, a star doesn't do that. A star burns, right, and it releases energy. To get anything heavier than iron, you need to put energy in. Okay, that's what that diagram there is showing. You see, see how everything peaks out at iron, and then the amount of energy released goes down when you do fusion. So where does that energy come from to create things like lead and uranium and gold and mercury and copper and rubidium and polonium and plutonium and blah, 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 blah. Where does all that energy come from? It comes from supernovas. Here's another supernova gift. Okay, it comes from supernovas. So what's kind of cool about this is that the fact that there is copper and mercury and gold and platinum and blah, 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 blah. The fact that there's all those elements heavier than iron proves that before our solar system formed, there was a supernova in our vicinity that contributed all of these relatively heavier elements. And that's why there's an Earth that's made out of, because if there wasn't, we wouldn't have that. We wouldn't have the terrestrial planets, right? Because we need all those elements that were contributed from the supernova that preceded the formation of our solar system. Does that make sense? Because otherwise it would just be a pure hydrogen solar system. So we needed to have this supernova. We needed to have this supernova that preceded, almost undoubtedly preceded, we didn't observe it, but we infer that it must have existed. It must have preceded the formation of our solar system. Because remember, this is kind of cool when you think about it. Before our star was born, there were other stars that existed. They burned out, they lived their lives, and they died. And then our star came into existence. So there were whole stars that lived out their whole lives and burnt out and died, and then our star came into existence.
And that would be 16 or 15?
Stellar nucleosynthesis can create elements up to what atomic number? It was number 26, iron. What's the heaviest element that can be generated by nucleosynthesis? Does anybody get that? So it's iron, right? So how are elements heavier than iron formed? They have to be formed from a supernova, because the supernova provides the energy to make these heavier elements. Okay, and then what is the source of all of? And I said this earlier. What is the source of all of our solar energy? Where's all that solar sun energy coming from? What's making the energy? It's hydrogen. Mostly, it's hydrogen burning. But it's this process of stellar nucleosynthesis. Mostly hydrogen burning, but also the triple alpha process, carbon burning, et cetera, contribute smaller amounts of energy. But it's mostly hydrogen burning. Oh, here's that GIF I was looking for. Yeah, and then the hydrogen comes together, so you push them closer and closer and closer together. Pressure increases, and then they fuse. Okay, so that's how you go from an early solar nebula to a sun, a proto-sun. Okay, so it's the pressure increases until it ignites the hydrogen through pressure. It ignites it through pressure. And that just comes from the gravity, because the nebula just gets too big. It just grows too much. Okay. So that's kind of maybe like an artist's depiction of maybe what the sun and their solar system first looked like when it ignited, the sun first ignited. You can notice that instead of planets, we have all this like dust, right, swirling around. So that's the early solar nebula. So all this dust eventually accreted together, right? And what did the dust look like? What did that stardust look like? It was all just, it was like little fragments of rocks and ice and minerals and things like that that eventually accreted together and made the planets.
Like a rock tumbler?
Huh?
Like kind of like a rock
Kind of,
tumbler?
yeah, sure, maybe like a rock tumbler, except things were kind of gluing together and sticking together and accreting together. Instead of having a bunch of dust, started to grow, gravitationally grow and create planets. Some of those planets banged into each other and blew up, and that's why you have that piece of the core of another planet, right? Okay, so here are some pieces of meteorite you can look at. So this first one is it's a black rock, and maybe it even kind of looks like the basalt that you saw, but it's not basalt at all. It's a piece of the meteorite, a very famous meteorite called Allende. It's been very much studied, and the reason that it's been very much studied is because it's a very good representation of what this early solar nebula dust would have been like. So you can imagine this little piece of Allende is very, very much what this material would have been like that's spinning around. Okay? So you can look at it and be like, oh, you could say to yourself, oh, that's a black rock, or you could say, but it's like this stuff, right? So it kind of shows the origins of Earth and everything. So that's Allende. And then coming around also is a beautiful little piece of a iron meteorite. And you'll actually see the iron meteorites are actually, like I said, they're the cores of planets that are gone. They've blown up. They've collided with each other. They've blown up. And the iron of it, you'll see this crosshatch pattern. If you look closely at the iron meteorite, you'll see that crosshatch pattern. Can you see what I'm talking about, Samantha?
Mm-hmm.
There's that crosshatch pattern. That's the iron-nickel alloy. That's the iron and the nickel crystals interweaving and growing together. So it shows you the composition of the iron and the nickel. It's kind of cool. Okay. So anyway, I gotta move on here. All right, let's talk about also the ice line. You have a question about the ice line there, right? So ice line's important for us. So the ice line is it's the point in the solar system in which ice, like kind of more volatile elements, like gases, could condense and form into an ice, form into a solid. So it's like a temperature line. Okay, when you're on the outside of that line, you get condensed CO2, right? So think of dry ice. We're talking about like dry ice, condensed CO2, solid CO2. CH4, that's ammonia, it's a methane. N2, that's nitrogen. So this is all like super cold stuff, right? It's very, very cold. Think of dry ice, right? Think of like, has anyone ever seen like liquid nitrogen before, right? Liquid nitrogen, it's really, really cold. Okay, so that only occurs when you get so far out, right? And you have to get about 5 times further from the sun than we are to get that cold. So that's why on the inside of the planets, okay, we have Mercury, Venus, Earth, Mars, right? What are they made of? They're made of rock and metal, okay? When you get beyond that, what do you get? You get Jupiter, yeah, Saturn, Neptune, Uranus, Neptune, right? What are they made of? Are they made of rock and metal? No, they're made of like gaseous elements, right? So like methane, CO2, nitrogen, carbon dioxide, okay? Why do they form like that? It's because they formed outside of the ice line where those kinds of elements, what we call more volatile elements, could condense. Does that make sense to everybody? Or is it just, okay, been going on an hour, I'm so sorry. Getting, all right. I'm almost done, I'm sorry, this goes on a long time. All right, so how does the composition of planets within the ice line differ from those like on the outside of the ice line, right here? So on the inside of the ice line, when you're closer to the sun, what's the composition of the planets like? Mercury, Venus, Mars, Earth, or Mercury, Venus, Earth, Mars, I mean. It's rock, right? Rock and metal, okay? Rock and metal have a really high melting temperature, right? But then you have things on the outside of the ice line that are like CO2, methane, carbon dioxide, nitrogen. Those things have a lower melting temperature, and they form out there, way out there, beyond the ice line because it's colder. Okay? Very important for us because we wouldn't have oceans. We can't have oceans on the outside of the ice line. So there's the ice line. Okay, there you go. See, the ice line, you got the rocky planets, then there's the ice line, and then you have the gaseous, icy, and gas planets. So all that makes sense. You got number 17, 18. Okay, so planets formed by, how'd the planets form? They formed by accretion. So what is accretion? It's very simple. It's just that as planets grow, they are sucking in, gravitationally sucking in more and more and more of those meteorites, right? They're sucking them in. They're sucking in things that are asteroid-sized and everything from dust to small planets. So everything from dust to small planets, and it's quite possible that Earth even sucked in a couple, maybe 1 or 2 small planets in our history. So, you know, a lot of people think that's how the moon formed, and it's possible that that is how it formed. So anyway, that's accretion. It's just gravitationally, a planet is sucking in all the dust and all the material that's in its orbital zone. That's around it. Okay. So does that all make sense to people? Okay, here's a kind of obvious question. When meteorites hit the Earth like this, does that release a lot of energy? Is there a lot of energy released when that happens? When the meteorites strike Earth?
Yes.
Yes, right? A lot of energy, right? So I know it's obvious, but it's true. All that energy. Now you know that it's hot inside of the Earth, right? We have a lot of energy inside the Earth. Where did all that heat come from? Why is it hot down there? I mean, what? How did it get so hot? What's that? So the heat, it's actually what we call primitive heat, primordial heat, that comes from the original accretion energy. It's from all those meteorites over the millions of years striking Earth, heated up. It's all actually gravitational energy. Came from these meteorites, small planets, asteroids. It's all accretionary energy. We call it primordial energy because it's kind of like original, primal, the energy that you started off with. So that's why it's hot inside the Earth. Can anybody think of the other? Because I asked for two sources of Earth's heat. So one of them is this accretionary energy, primordial energy. Another, it comes from another source. Can anyone think of another possible source of energy? What's that? The sun? Well, the sun is, yeah, the sun helps, but that's not the main, because I'm talking about the inside of the Earth now. Core, and there's a lot of good guesses here. What's that? Convection, it's a good guess too, so I'll give it to you. It's actually from, these are all good ideas. It's actually from radioactive decay of the different elements, because there's uranium in the core, potassium, by the way, a lot of potassium, you may not know this, but a lot of potassium is radioactive too. So there's potassium down there. There used to be a radioactive isotope. It's no longer with us anymore, but there used to be one called aluminum-26. It's gone now. But aluminum used to be, isn't that crazy? Aluminum used to be radioactive. It's all decayed now. But there used to be aluminum. So all that energy from the radioactive decay also heats up the interior of the Earth. So it's from radioactive decay and it's from accretionary energy. Okay, so now we have Earth. Now we know kind of where Earth's energy came from and how Earth formed and how the solar system formed and how the universe formed. Blah, 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 blah. Here's a picture showing maybe like a protoplanet colliding with Earth early in its possibly could have happened now. Had a small planet colliding with Earth, Mars-sized or something, Moon-sized or Mars-sized colliding. And that's where we get this. We know that happened. We know it happened in the solar system because that's why we have these iron meteorites. They are cores of planets. Okay, so that could have been Earth 4.5 billion years ago when we first started off. It was probably, a lot of it was probably liquid magma and liquid metal. So is that a good place to have an ocean? Do you think you could have an ocean there? Right now, because things had to cool down, right? So the solar system had to stabilize, which probably took a few hundred million years for things to stabilize and calm down, where we didn't have like constant cataclysmic meteorite collisions, and the surface could cool down enough to have liquid water stable on it. Okay, so there's all the meteorites. Okay, that's how the core formed. I don't ask about formation of the core. You don't have to know about that necessarily. So anyway, now you might know that a lot of water is released from volcanoes. Actually, you've probably seen things like this, volcanoes, and they're releasing a lot of gases, right? I'm almost done. They're releasing a lot of gases, a lot of H2O. A lot of that gas is water. Okay, so a big source of Earth's water was probably from this volcanic outgassing. Okay, so that's probably one source of Earth's water. So outgassing of the mantle, right? So there's a volcanic eruption off the coast of New Zealand. A lot of this gas that's being released, it's just water. 70 to 95% of the gas released from a volcano is water. So that's probably a big source of Earth's water. So you do that over 100 million years. Going to build up a lot of water on Earth's surface. Okay. Now, another hypothesis that still has quite a bit of traction is that, because you have to wonder about this, Mercury, Venus, Mars, no water. Earth, water. So why is there water here? Another popular hypothesis is this, is that there was a comet collision, maybe there were multiple comet collisions early in Earth's history that provided some of the source of water. That's another idea. Which people kind of like that hypothesis because it explains why we have water and Venus doesn't. We are not very different than Venus. I mean, as a planet, we're very similar in size. We're very similar in our orbit around the sun. So that hypothesis sort of explains why we have it and other planets don't. So it's just an idea. Now, sorry, I don't have a slide on this, but another hypothesis too, because again, scientists, we're trying to understand why do we have water, the other planets, terrestrial planets do not. Another idea is that for whatever reason, there was more liquid water in the material that was surrounding our orbital zone, and it was sucked in during accretion. And so that was yet another set. There just happened to be more water-rich minerals in the orbital zone around that eventually became Earth. Does that make sense? It's just, I've got to make a slide for that.
Can you say that again?
Sure, I'll say it one more time, so I don't have a slide. So there just happened to be, we don't really know why, but perhaps there just happened to be more water-rich minerals that were in the orbital zone of Earth as it accreted. So that's another idea about why we have water and Venus doesn't, or why Mars doesn't. Venus is really more of a question, why Venus doesn't have water. Okay? Now, another thing I want to talk about, one last thing. What was the atmosphere like? That's the last question. So when we started off, what was the atmosphere like? And this was way long time ago, 4 billion years ago. What was the atmosphere like? Hydrogen, helium, ammonia, methane, a lot of nitrogen. You know that our atmosphere is 78% nitrogen, right? It's actually mostly nitrogen. So what you're breathing in and out at any given time is mostly nitrogen. Carbon dioxide, lots of water. There's probably lots of water in the atmosphere at that time. But what element is missing here?
Oxygen.
Oxygen. And why is oxygen missing? In the early Earth.
There was a plant life.
There wasn't plant life. So oxygen in the atmosphere comes from photosynthesis. Oxygen in the atmosphere comes from photosynthesis. Oxygen in the oceans, I mean free oxygen, not H2O oxygen, but free oxygen, dissolved oxygen, comes from plant life, from photosynthesis. So we had to wait for photosynthetic organisms to evolve before we got free oxygen in the atmosphere and in the oceans. Okay, so that's maybe what it looked like early. So probably by about 3.8 billion years, we had liquid water, we had oceans. There was probably also a time in Earth's history in which you actually need water to create continents, by the way. We'll learn this later. You need water to create continents. So there's probably a point in Earth's history in which it was a total water world. It was just water. There wasn't even continental land. So it started off as all ocean. Okay. I just want to point this one last thing out. How long ago did we get those oceans? About 3.8 billion years ago. We know that because we have pillow basalts. Remember I passed around basalt, right? We have seafloor basalts that are left over from 3.8 billion years ago that are very indicative of ocean floor. So we think that this is pretty definitive evidence that we had oceans for 3 billion years. Okay, there you go. There's pillow basalt. Okay, so I took all the time. Usually I finished early, but so anyway, have a good. This is Wednesday, so yeah, have a good weekend, right? I'll see you Monday. Don't forget to do your discussions, and you can leave your lecture assignment number
Yeah, that's
4.
right. I picked that up.
I'll pick that up.
Sharp.
So you're having a meeting today?
Yep, 3 o'clock.
3 o'clock?
Yeah. It's 332, or you can meet in 303, which is, well, I mean, I'll just be going around. But my office is 332 next to the bathroom, and like right down the hall from there, there's 303. I was going to hold it for 303. See you there.
Is your shirt from Yellowstone?
Yes.
I love it.
I should be able to turn in the lecture assignment early.
Oh, okay. You wanted to turn those in?
Oh, I don't know.
Okay, go right ahead. You can just leave them, yeah, pass them stuff at the desk.
Okay, I'm just gonna stay with my two.
No problem, go
Thank
for it.
you.
Oh, do you have a statement? Do you see it?
Can we run by the discussion, like, the one of the findings?
Yeah,
before
sure.
posting it? Okay. See you later.
Yeah, later.